Hello everyone, my name is Yuju Yu. Today I'm going to talk about my work, Semi-Supervised Domain Adaptation with Source Label Adaptation. In Semi-Supervised Domain Adaptation, we leverage data from the source and target domains to extract invariant features across both domains. However, training the model directly with source and label target data may suffer from the domain shift issue. In this case, the 7th class in the source data misaligns with the 59th class in the target data. To address this challenge, we propose source label adaptation, a novel source adaptive paradigm for semi-supervised domain adaptation. We view the source data as a version of the target data with noisy labels, and we aim to correct the source labels with the estimated target centers. The framework can be easily coupled with the current state-of-the-art methods, and the results on two SSDA approaches show superior performance across benchmark datasets. Let's talk about the motivation. Our goal is to find an ideal model G-star that can minimize the target risk. Suppose we have access to this ideal model. For each source data access, G-star of access is the most suitable label that best matches the ideal target space. The below illustration actually hints us that to build an ideal target space, source data is not necessary to be well clustered. As we mentioned earlier, we view the source data as a version of the target data with noisy labels. Thus, we propose to adapt the original source label YS to the ideal label G-star of access. The challenge is that we are not able to access the ideal model G-star. Instead, we have to approximate it through the current estimation of the unlabeled target data. To easily build a classifier from the target view, we borrow the idea from prototypical network. The key idea behind a prototypical network is to identify the center or prototype of each data class in a feature space. This prototype serves as a representative point for that class. When making predictions, the network measures the distance between a data point and each prototype, using this information to determine the most likely class assignments. Recall that our goal is to build a model that offers a perspective from the target data. In our case, we have access to a few target data. Thus, we can build a protonet with target centers. But the challenge is that, comparing to the massive amount of the unlabeled target data, we usually have only 1 or 3 shots for each class, making the estimation less accurate. To address this, we propose the protonet with pseudo centers. The key idea of protonet with pseudo centers is to develop a model that offers a more precise target perspective. Initially, we determine the pseudo label for each unlabeled target data. Then, we find a pseudo center for each class and construct a prototypical network based on these centers. We conduct a comparison by measuring the average altitude distance between the ideal centers and both the labeled target centers and its pseudo centers. The result shows that the pseudo centers are significantly closer to the ideal centers, indicating that pseudo centers should be a better agent of the ideal centers. Although we build a protonet with pseudo centers to provide a view from target data, it is still an estimation of the ideal model. Thus, we introduce a hyperparameter alpha to regularize the level of trust to this estimation. The adapted label tilde y is a convex combination between the original label and the suggested adapted label from PPC. Then, with the adapted label, we propose a label adaptation loss to replace the typical source loss function. Here H measures the cross entropy between two distributions. Traditional SSDA algorithms typically focus on exploring better use of the unlabeled target data. Our framework, on the other hand, explores the training of source data with adapted labels to better align with the ideal target space. As a result, our approach can be readily applied to other SSDA algorithms, effectively enhancing their performance. This is the overall architecture of our framework, source label adaptation. At each iteration, we first produce the adapted labels with the help of our label adaptation model, PPC, and calculating the label adaptation loss accordingly. Then, we can incorporate any state-of-the-art algorithm to further improve the utilization of the unlabeled data. Here we offer additional implementation details. The effectiveness of our label adaptation framework heavily depends on the quality of the predicted pseudolabels. However, the prediction from the initial model can be noisy. Thus, we introduce a runout stage W to obtain more stable pseudolabels. During the runout stage, we refrain from calculating adapted labels and keep the labels unchanged. Another concern arises regarding the update of pseudo-labels and pseudo-centers. During the training phase, the feature space keeps changing from every iteration. If the centers are not updated accordingly, the quality of the estimated pseudo-centers would progressively deteriorate. To address this, at certain intervals, we re-estimate the pseudo-labels and centers based on the current feature space, ensuring their alignment remains accurate. To validate the effectiveness of our method, we employ our framework in two representative SSDA algorithms, MME and CDAC. Through comprehensive comparisons with other state-of-the-art algorithms, our approach demonstrates superior performance on both domain name and office home datasets. Please refer to our main paper for more experimental results. To demonstrate the change of labels, we visualize the top 3 probabilities of the adapted labels on 2 classes. For the backpack case, SLA suggests to adapt the label from 100% of backpack to 30% of backpack and 5% of toys and 4% of keto. After source label adaptation, the adapted labels are indeed much closer to the ideally adapted labels. We can draw the same conclusion for the naive class. Here we plot the intermediate results in MME plus SLA during each iteration. The red line stands for the original MME. The orange line represents the application of PPC right after MME. The blue line indicates the performance of MME with our proposed SLA framework, and the purple line represents the performance of PPC within MME plus SLA. As we can see, PPC is actually a strong enough model that has performed well on the target domain at the early stage. However, without updating the source labels, it will end up converged to the same performance as the original MME. On the other hand, in our SLA framework, the model leverages the benefits of PPC, resulting in better performance. Finally, let me conclude our work. We present a general framework, source label adaptation for semi-supervised domain adaptation. We can easily apply our framework to other SSDA algorithms. We rethink the usage of source data and approach domain adaptation as a noisy label learning problem. In the empirical results, our method improved to representative SSDA algorithms, MME and CDAC, on 2 major datasets for both 1-shot and 3-shot settings. Please visit our project page for more details and information about our work. The code has also been made publicly available. Thank you.